January 17, 1943, Stockholm, Sweden, 2:14 a.m. The snow falls in silence outside the apartment window on Strandvägen. Inside, a man named Henrik Lindström sits at a wooden table, his hands trembling not from cold, but from the weight of what lies before him. Technical drawings spread across the surface like forbidden artifacts, German engineering specifications, ballistic coefficients, metallurgical composition charts. The room smells of cigarette smoke and ink. His breath forms small clouds in the unheated space. Through the wall, he can hear his neighbor's clock ticking, each second a reminder that discovery means death. The Gestapo has operatives even here in neutral Sweden. Lindström presses his palms flat against the table to steady them. He is 42 years old. He is not a soldier. He is a metallurgical engineer who once designed mining equipment in Gothenburg. Now he is something else entirely. Now he is a thief of secrets, and the blueprints before him represent the most advanced artillery piece Nazi Germany has produced, the 8.8mm Flak 41. He has 6 hours to photograph every page before the documents must return to their source. 6 hours before the courier arrives. 6 hours before this information can begin its journey to London, where men in uniform will study what he has stolen and perhaps build something to answer it. Lindström's path to this moment began not with ideology or patriotism, but with horror witnessed through proximity. He had been in Hamburg in 1941, consulting for a Swedish steel firm that supplied Germany's industrial machine. He had seen the labor camps on the periphery of the city. He had watched skeletal men load cargo at the docks under the clubs of guards. He had heard the sounds that came from behind factory walls, where prisoners worked until they collapsed. When he returned to Stockholm, he could not sleep. When British intelligence approached him 6 months later, a careful conversation in a bookshop on Birger Jarlsgatan, he said yes before they finished asking. They trained him in basic tradecraft, dead drops, recognition signals, how to use a Minox miniature camera, how to memorize technical specifications in case documentation proved impossible to secure. They told him his value lay not in gathering military intelligence, but in understanding what he saw. An engineer could recognize significance where a trained spy might see only numbers. His contact inside Germany is a man he knows only as Ernst, a German himself, though Lindström suspects this is not his real name. Ernst works in the procurement office of Krupp's Essen facility, the sprawling armaments complex that feeds the Wehrmacht's appetite for steel and fire. Ernst is the one who brought these drawings to Stockholm, hidden in a false-bottomed briefcase carried across the Baltic on a Swedish trade vessel. Ernst is the one who will face the noose if this operation unravels. Lindström thinks of this often. He thinks of Ernst's family, whom he has never met and never will. He thinks of the invisible web of people who risk everything so that these sheets of technical paper might cross from one side of the war to the other. The Flak 41 represented a significant evolution in anti-aircraft artillery design, where its predecessor, the legendary 8.8mm Flak 1836-37, had dominated battlefields from Spain to Stalingrad. The Flak 41 pushed the boundaries of what rapid-fire heavy cannon could achieve. Its barrel length exceeded 7 meters. Its muzzle velocity approached 1,000 meters per second. The shells it fired could reach altitudes of 14,000 meters, well into the operational ceiling of Allied strategic bombers. More critically, its rate of fire, 25 rounds per minute in optimal conditions, made it a devastating threat to aircraft formations. The Germans had mounted these weapons on railway cars, on concrete flak towers in Berlin and Hamburg, and on experimental self-propelled chassis, but production remained limited. Complex manufacturing requirements, precision tolerances, and material shortages meant only 500 units had been completed by early 1943. The Wehrmacht wanted thousands. What Lindström studies now is not just one weapon system, but the crystallized knowledge of German metallurgy, ballistics theory, and industrial design philosophy. He adjusts the Minox camera on its miniature tripod. The lighting must be perfect. Too much shadow and the technical annotations become illegible. Too much glare and the photographic emulsion washes out. He has practiced this in his own apartment with newspapers and magazines until the process became mechanical. Focus. Steady the frame. Advance the film. 24 exposures per roll. He has brought 8 rolls, 192 potential images. The blueprints before him number 37 sheets. He must photograph each one multiple times to ensure legibility, to capture every detail, every dimension, every material specification. The gun's breech mechanism alone occupies 4 technical drawings. each showing the component from different angles, each annotated with German engineering abbreviations that he translates mentally as he works. Federung for spring mounting, Rücklaufbremse for recoil brake, Rohrrücklauf for barrel recoil mechanism. The design philosophy embedded in these drawings reveals German engineering at its most sophisticated and most constrained. The Flak 41's three-section barrel allowed for easier transportation and replacement of worn sections without discarding the entire tube. The semi-automatic breech mechanism, adapted from earlier Rheinmetall designs, used a horizontal sliding block that opened and closed with mechanical precision, ejecting spent casings and chambering new rounds in a continuous cycle, as long as the loader could feed ammunition. The carriage, a cruciform platform that deployed 4 outriggers for stability, could traverse a full 360 degrees and elevate from -3 to 90 degrees, allowing the gun to engage targets from ground level to directly overhead. But the drawings also showed something else: the compromises imposed by wartime exigency. Certain components specified steel alloys that Lindström knew were expensive and difficult to produce in quantity. Others showed tolerance requirements so tight that only the most advanced machine tools could achieve them. This was a weapon system designed for an industrial base that was beginning to fracture under Allied bombing and resource depletion. What made these documents invaluable was not merely the weapon specifications, but what they revealed about German capabilities and limitations. British and American intelligence analysts would study these drawings to understand not just how to counter the Flak 41, but how to assess German manufacturing capacity, metallurgical resources, and design priorities. They would reverse engineer German thinking. They would look for weaknesses, components prone to failure, materials that could be targeted through strategic bombing, production bottlenecks that could be exploited, and they would steal what worked. The Allies were not above learning from enemy innovation. Lindström photographs through the night. His fingers grow numb despite the gloves he wears to avoid leaving prints on the documents. The camera clicks with mechanical rhythm. Outside, Stockholm sleeps under occupation's shadow, neutral in name, but threaded through with intrigue from all sides. German diplomats walk the same streets as Allied intelligence officers. SS officers on leave visit the same restaurants as Norwegian resistance fighters planning sabotage. Sweden trades with Germany, sells iron ore that becomes tank armor and artillery barrels, while simultaneously allowing its territory to serve as a corridor for intelligence and escaped prisoners making their way to Britain. It is a delicate balance, a nation walking a tightrope, while Europe burns on either side. By dawn, he has finished. Every page photographed multiple times, every detail captured. He returns the drawings to their portfolio case exactly as they were arranged. Ernst will collect them at 8 o'clock. By noon, they will be back in Essen, filed away in Krupp's technical library, and no one will know they ever left. Lindström packs the film rolls into a hollowed-out book, a Swedish translation of Goethe's Faust, appropriately enough. The book goes into his briefcase. The briefcase will go with him on his morning walk. In Humlegården Park, he will sit on a specific bench and read his newspaper. Another man will sit beside him. They will not speak. When Lindström leaves, he will forget his briefcase. The other man will remember it for him. By evening, the film will be in the British Embassy. By the following week, it will be in London. He washes his face in cold water. The mirror shows a man who has aged years in months. He wonders if Ernst looks the same. He wonders how many more times they can do this before probability catches up with them. The Gestapo is not incompetent. The Abwehr, German military intelligence, has broken Allied networks before. People disappear. Messages stop coming. You never know if your contact was arrested or simply reassigned. You never know if the person you're supposed to meet is still trustworthy or has been turned. Now working to reel in everyone connected to the network. The strategic implications of intelligence operations like Lindström's extended far beyond the immediate tactical value of stolen blueprints. Modern warfare, by 1943, had become as much a contest of information and industrial capacity as of battlefield courage. The side that understood enemy capabilities could adapt, innovate, and allocate resources more effectively. When British intelligence received Lindström's photographs, the documents would flow to multiple analytical teams. Ordnance specialists would study the gun's mechanical design. Metallurgists would analyze the specified alloys to understand German access to strategic materials like tungsten, molybdenum, and chromium. Production engineers would estimate manufacturing time and facility requirements. Ballistics experts would calculate the weapon's performance envelope and develop countermeasures, optimal bombing altitudes, evasive patterns, electronic countermeasures if radio proximity fuses were involved. But the crown jewel of this operation was not merely acquiring German secrets. It was what the Allies would do with them. The Flak 41's design contained innovations worth adapting. Its high muzzle velocity stemmed from chamber pressure optimization and barrel metallurgy advances. Its rate of fire derived from breech mechanism efficiency. These lessons could inform Allied weapon development. The British were already working on improved anti-aircraft systems. The Americans were producing weapons in quantities that dwarfed Axis output, but constantly sought performance improvements. Intelligence like this accelerated development cycles, allowed engineers to leapfrog research phases, and prevented duplication of effort. Moreover, understanding the Flak 41's deployment patterns would help Allied bomber planners. If intelligence could determine where these weapons were stationed, which cities, which facilities, which transportation networks, targeting priorities could adjust accordingly. Bomber streams could route around known Flak concentrations. Suppression missions could target identified battery positions. The intelligence war and the shooting war were inseparable. 3 weeks later, in a workshop buried beneath London, British engineers examine enlarged prints of Lindström's photographs. The facility is part of the Ministry of Supply's sprawling apparatus for weapons research and development. Concrete walls keep the sounds of industry from reaching the street above. Bright electric lights illuminate drafting tables where men in shirt sleeves pore over German technical drawings, as if reading sacred texts. One of these men is William Chambers, a 56-year-old artillery designer who learned his trade in the Great War and spent the interwar years developing weapons that were obsolete before they left the drawing board. Always underfunded, always ignored until too late. Chambers holds a magnifying glass over one section of the Flak 41's breech mechanism drawings. He makes notes in a leather-bound journal. Around him, other engineers debate interpretation of German technical annotations. Precision of translation matters. A millimeter's error in understanding a dimension or a misidentified alloy specification could invalidate the entire analysis. Look at this bearing assembly, Chambers says to his colleague, Martin Davies. They've solved the heat dissipation problem we've been fighting with the 3.7-inch. See how they've channeled the gas flow? Davies leans in. He sees it. The German designers had created a gas deflection system that channeled propellant gases away from critical bearing surfaces, extending component life and maintaining accuracy through sustained firing. It was elegant. It was something British designers had been attempting for 2 years with limited success. Can we adapt it? Davies asks. We'd have to retool the entire breech assembly, Chambers replies. But yes, 6 months, maybe less if we prioritize it. They work through the night. As Lindström had done, different men separated by 1,000 miles and an invisible war, united by technical problems that transcend ideology. Chambers does not know Lindström exists. He knows only that these documents came from a reliable source and that people risked their lives to acquire them. He treats the work with appropriate gravity. The British gun development program had been troubled since the war's beginning. The 3.7-inch anti-aircraft gun, designed in the 1930s, was effective but not exceptional. It lacked the altitude reach of German heavy flak. Its rate of fire was adequate but not overwhelming. Most critically, British production had been slow to ramp up, plagued by manufacturing complications and resource allocation disputes between services. The Royal Navy wanted guns for ships. The Army wanted guns for homeland defense and field deployment. The RAF wanted resources directed toward fighter production and radar systems. Every gun built represented steel, machinery hours, and labor that could not be used elsewhere. The entire British war economy was a vast exercise in triage and compromise. The German blueprints offered a path forward. Not copying the Flak 41 directly, that would require retooling factories for metric specifications and German components, but adapting its innovations to British manufacturing capabilities and design standards. Chambers began drafting proposals for a new weapon, tentatively designated the 3.7-inch Minke III, that would incorporate German breech efficiency, improved barrel metallurgy, and enhanced traverse mechanisms, while remaining compatible with existing British carriages and fire control systems. But Chambers was also thinking beyond anti-aircraft applications. The Flak 41's high-velocity gun technology had implications for anti-tank warfare. German armour was growing thicker, more sophisticated. British tank guns struggled to penetrate the frontal armour of Tigers and Panthers. A weapon derived from flak gun technology with its high muzzle velocity and penetration capability, could be adapted for anti-tank use. This was not a new concept. The original 8.8 cm Flak had famously been pressed into anti-tank service in North Africa, where Rommel's gunners discovered that weapons designed to destroy aircraft at high altitude were equally effective at destroying tanks at ground level. The German 8.8 had become legendary, feared by Allied tank crews who learned that engaging one meant death before you got within effective range to return fire. Chambers envisioned something similar for British forces, a gun that could serve dual purposes: anti-aircraft defense and anti-tank direct fire. The logistical advantages were obvious. One weapon system, one training program, one supply chain. But the technical challenges were substantial. Anti-aircraft guns required high elevation and traverse rates, automated fusing and sustained fire capability. Anti-tank guns required pinpoint accuracy, armor-piercing ammunition, and low-profile carriages for concealment. Combining these requirements in one system demanded compromises that might make the weapon mediocre at both missions, rather than excellent at one. Nevertheless, the concept gained traction. By March 1943, Chambers had preliminary designs on paper. By May, the Ministry of Supply had approved prototype construction. The first test firing occurred in July at the Shoeburyness Proving Grounds on the Thames estuary. The results were promising but not revolutionary. The new gun achieved the desired muzzle velocity. Its rate of fire exceeded expectations, but reliability issues emerged. The adapted German breech mechanism, translated into British manufacturing tolerances and materials, proved temperamental. Failures occurred after sustained firing. Extractors jammed, gas seals leaked. This was the reality of wartime weapons development. Theoretical designs confronted manufacturing limitations, material shortages, and the unforgiving physics of combustion and metallurgy. Engineers returned to their workshops. They revised. They tested again. The process consumed months while men died on battlefields where better weapons might have saved them. This was the hidden cost of innovation. Time measured in lives. Meanwhile, the intelligence war continued. Lindstrom photographed more documents. Ernst delivered them, took them back, moved through his days at Krupp with the knowledge that exposure meant torture and execution. The network operated in other cities: Zurich, Lisbon, Istanbul. Other engineers, other spies, other stolen secrets flowing across borders. The Germans did the same, of course. Intelligence was mutual thievery, each side plundering the other's innovations, each side paranoid about penetration and betrayal. By autumn 1943, British factories were producing what had become known internally as the improved 3.7-inch gun. It was not revolutionary. It did not win the war in a single stroke. But it was better than what had come before. It could engage higher altitude targets. It could fire faster. It could, in desperate circumstances, destroy German armor at battlefield ranges. Thousands were produced. They deployed to anti-aircraft batteries defending London and industrial cities. They went to North Africa and Italy with the 8th Army. They stood on Channel beaches as D-Day approached, ready to contest German air power over the invasion beaches. No official record credited Henrik Lindstrom. No citation mentioned Ernst. The men who used these guns never knew that Swedish snowfall and German blueprints and a metallurgical engineer's trembling hands were part of the weapon's genesis. This is how intelligence operations work. Invisible threads connecting decisions to consequences, causes to effects, with all the names redacted and all the stories classified. But the story extends beyond weapons and battles. It encompasses the fundamental transformation of warfare itself during the Second World War. Previous conflicts had been won through courage, tactics, and material weight. This war added new dimensions: information supremacy, technological innovation, industrial sophistication. The side that could steal secrets, adapt enemy innovations, and translate intelligence into operational advantage held an edge as important as divisions in the field. The Manhattan Project was born from refugee scientists carrying theoretical physics knowledge out of Europe. Radar development accelerated through captured German equipment and interrogated engineers. Cryptography battles, Enigma, Purple, the entire invisible war of codes and ciphers determined convoy routes and battle plans. Intelligence was not supplementary to warfare, it was warfare's central nervous system. The Flak 41 itself became almost mythological among Allied aircrew. They learned to recognize its distinctive sound, the sharp crack of its high-velocity shells detonating at altitude. They learned to fear the vertical tracer columns rising from German cities, each line of fire a potential death. They learned evasive patterns and attack profiles designed to minimize exposure time within the gun's engagement envelope. The psychological dimension of weapons cannot be quantified in technical specifications. A gun that inspires fear affects crew performance, decision-making, mission outcomes. Men fly differently when they know what hunts them. German production of the Flak 41 never reached intended levels. The weapon's complexity worked against it. As Allied bombing intensified, German factories struggled to maintain production of any weapon system, let alone one requiring precision manufacturing and exotic materials. The simpler Flak 1836-37 remained the Wehrmacht's primary heavy anti-aircraft weapon throughout the war, produced in greater numbers because it demanded less and worked reliably. The Flak 41, for all its sophistication, was a victim of Germany's deteriorating industrial situation. By 1944, many batteries were equipped with whatever could be scrounged. Obsolete guns, captured weapons, experimental prototypes pressed into service before testing was complete. The Third Reich's vaunted engineering excellence could not overcome strategic reality. Germany was being outproduced, outmaneuvered, and outfought on all fronts. But the knowledge embodied in those blueprints lived on. After the war, Allied technical intelligence teams swept through Germany, seizing documents, interviewing engineers, dismantling facilities to understand exactly what German industry had achieved. The Flak 41 was among thousands of weapon systems analyzed in exhaustive detail. American and British engineers produced comprehensive technical reports that influenced post-war weapon development. Soviet teams did the same, hauling entire factories back to the USSR, relocating German engineers to continue their work under new management. The technological legacy of the Second World War extended decades into the future, shaping Cold War arsenals and strategic thinking. Henrik Lindström survived the war. He returned to his previous life, or something resembling it, working again in Swedish metallurgy and mining equipment design. He never spoke publicly about his intelligence work. The British awarded him no medals. Secrecy demanded silence. Ernst's fate remains unknown. Records were destroyed, memories unreliable, and the chaos of Germany's collapse erased many stories that will never be recovered. Perhaps he survived. Perhaps he was caught, his name appearing in some Gestapo file that burned in Berlin's final days. This is the nature of clandestine operations. Participants vanish into history's shadows, their contributions unrecorded except in classified archives that may never be opened. The broader narrative encompasses an essential truth about modern conflict. Victory depends not merely on who fights, but on who knows, who learns, who adapts. The Second World War was won by millions of soldiers, sailors, and aircrew who fought with extraordinary courage. But it was also won by engineers who designed better weapons, by intelligence officers who stole enemy secrets, by factory workers who outproduced their adversaries, by scientists who harnessed physics for destruction. It was a total war in the most complete sense. Every aspect of national existence mobilized, every advantage exploited, every weakness probed. The artillery pieces that descended from Lindström's stolen blueprints fired their last shots in anger decades ago. They stand now in museums. If they survived scrapping, their mechanisms frozen, their purposes obsolete. Modern anti-aircraft systems use guided missiles, radar targeting, and computer fire control that would seem like sorcery to the men who served flak guns in 1943. But the fundamental principles remain unchanged. Warfare is a contest of capabilities and countermeasures, innovations and adaptations, each side striving to understand and overcome the other's advantages. Intelligence remains warfare's foundation, the invisible architecture on which tactical and strategic decisions rest. William Chambers lived until 1961. His papers, archived at the Imperial War Museum, contain detailed technical notes on German artillery systems, including extensive documentation of the Flak 41. Researchers studying these documents will find careful annotations, calculations and sketches showing how German innovations were understood and adapted. They will not find Lindström's name. They will not find Ernst's. The trail goes cold where secrecy demanded, and perhaps that is appropriate. Some stories are not meant for full telling, not because they lack importance, but because the people who lived them preferred silence. The guns built from stolen knowledge defended London. During the V-1 flying bomb campaign of 1944, they shot down German aircraft over Normandy. They stood in fields and on rooftops. manned by soldiers who never knew that Swedish winter nights and German blueprints were part of their weapons' hidden history. This is legacy in its purest form. Impact without acknowledgement, influence without credit, decisions whose consequences ripple outward long after the decision-makers are forgotten. Consider the mathematics of espionage and technological theft. One man, one engineer, one set of blueprints, thousands of guns built from derived knowledge, tens of thousands of shells fired, hundreds of aircraft engaged, some destroyed, some driven off, mission effectiveness degraded, bomber crews saved because their aircraft flew above flak ceilings that British guns could now reach. Ground forces protected because improved anti-tank capability meant German armour could be contested at longer ranges. The calculus becomes overwhelming, the variables too numerous to track, but the pattern is clear. Small actions in hidden places generate enormous consequences in public ones. The Second World War reshaped human civilization in ways still unfolding. The atomic bomb, radar, jet engines, computers, antibiotics, countless technologies were developed or accelerated by wartime necessity. The global political order, the United Nations, the Cold War's bipolar structure, decolonization's acceleration, the modern configuration of power and alliances emerged from the war's outcome. But beneath these grand transformations were millions of individual actions. A spy photographing documents, an engineer solving technical problems, a soldier firing a gun whose origins he did not know. History is the sum of these moments, the aggregate of decisions made by people who could not see the full picture, who acted from duty or fear or hope or desperation, whose choices accumulated into the narrative we now call the past. The Flak 41, in German service, shot down Allied aircraft whose crews never returned. It killed men who had families, who had futures that ended in fire and fragmentation over hostile territory. The improved British guns, derived partly from stolen German knowledge, did the same to Luftwaffe crews. Technology is morally neutral. Its use defines ethical character. The guns themselves were instruments, neither good nor evil, merely effective or ineffective at their designed purpose. What mattered was the cause they served and the hands that aimed them. Lindström understood this. In the few interviews he gave late in life to trusted historians, he expressed no pride, no satisfaction. He spoke of necessity, of horrors witnessed that demanded action, of conscience that would not permit neutrality when faced with absolute evil. He did what he could with the skills he possessed. Many did far more at far greater risk. Many died for less effect. The gradations of courage and sacrifice do not submit to easy ranking. Each person who resisted contributed what they could, and the sum of all those contributions was victory, purchased at unimaginable cost. The photographs Lindström took that January night in Stockholm travelled across borders and oceans, through hands and organisations, finally reaching people who could transform information into action. This is intelligence work distilled to its essence. The movement of knowledge from where it exists to where it is needed, across barriers designed to prevent exactly that transfer. The tradecraft, the dead drops, the coded messages, the false identities, exists to solve a fundamentally simple problem: how to tell someone something when powerful forces are dedicated to ensuring they never learn it. Modern intelligence services study these operations as case studies in successful espionage. They analyze what worked: Lindström's technical expertise, Ernst's access, Sweden's neutral geography enabling contact between agents and handlers, the Minux cameras enabling technology, the networks that moved film from Stockholm to London. They also study what failed in other operations: the networks that were betrayed, the agents who cracked under interrogation, the technical intelligence that proved false or misleading. The Second World War was a crucible for intelligence methodology, teaching lessons that informed Cold War operations and beyond. Yet for all the analysis, certain elements remain irreducible to technique. Courage cannot be taught from manuals. The decision to risk everything for a cause larger than oneself emerges from moral foundations that training cannot instill. Lindström and Ernst, and thousands like them, operated from conviction that transcended calculation. They understood the odds. They knew that capture meant torture and death. They did it anyway. This is the human dimension that analysis cannot fully capture, the variable that resists quantification. The gun blueprints were one operation among thousands. The Allied intelligence apparatus, British, American, French resistance, Polish networks, Soviet agents, defectors, and sympathizers generated enormous volumes of information throughout the war. Much of it proved useless. Some was deliberately false, planted by German counterintelligence. Some was accurate but irrelevant, answering questions no one needed answered. The art of intelligence lies as much in filtering and prioritizing as in collection. Having information means nothing if you cannot identify what matters and act on it before circumstances change. The analytical teams in London who processed Lindström's photographs understood this. They worked within a larger system that evaluated intelligence from multiple sources, cross-referenced claims, assessed reliability, and produced synthesized assessments for decision-makers. The blueprints were valuable because they could be verified. Technical specifications either work or they don't. Dimensions either match physical reality or they don't. Human intelligence, agent reports, and intercepted communications required more interpretation, more judgment about source reliability and potential deception. Technical intelligence, when obtained from primary sources like blueprints or captured hardware, had inherent credibility that other intelligence lacked. This distinction shaped how different intelligence types were utilized. Technical intelligence informed long-term planning, weapon development, industrial targeting, strategic resource allocation. Operational intelligence, troop movements, unit locations, attack plans, drove immediate tactical decisions. Strategic intelligence, enemy intentions, political developments, leadership dynamics, guided grand strategy, and diplomatic maneuvering. All types were necessary. All had limitations. All required skilled interpretation by experienced analysts who understood both the intelligence and the context into which it fit. The Flak 41 blueprints represented technical intelligence at its highest value. Detailed, verifiable, actionable information about enemy capabilities. British engineers could measure their own systems against German achievements, identify areas where the enemy held advantages, and determine whether those advantages could be overcome through adaptation or required entirely new approaches. This informed not just weapons development but tactical doctrines, training programs, and operational planning. If you know enemy capabilities precisely, you can fight smarter, not just harder. But intelligence has limitations. It reveals capabilities, not intentions. It shows what an enemy can do, not what they will do. The Germans had many weapon systems they never deployed effectively due to resource constraints, production delays, or strategic confusion. Intelligence analysts had to estimate not just German technical capability, but German industrial capacity to produce weapons in meaningful quantities, logistics capability to deploy them where needed, and tactical doctrine governing their employment. This required understanding the entire German war machine, not just isolated weapon systems. It required economic intelligence, political intelligence, and assessments of German strategic thinking. The blueprints were one piece of a vast puzzle. By 1945, as the war approached its conclusion, the Allies possessed comprehensive understanding of German military capabilities. They knew German weapon specifications, production rates, deployment patterns, tactical doctrines, command structures, and logistical constraints in extraordinary detail. This knowledge had been purchased through thousands of intelligence operations, millions of man-hours of analysis, and the courage of agents like Lindström and Ernst, who risked everything to provide information. The intelligence war had been won as decisively as the shooting war, though with far less public recognition. The atomic bomb's development was hidden from German intelligence throughout the war. The Manhattan Project's security was so effective that Germany never understood how close the Allies came to nuclear weapons capability. Had German intelligence penetrated the project and revealed its scope, German resources might have been redirected toward nuclear development or, more likely, toward destroying Allied nuclear facilities before weapons could be produced. Intelligence failure worked both ways. Germany failed to prevent Allied technological breakthroughs just as the Allies succeeded in learning German secrets. The side that protected its own innovations while stealing the enemy's held compounding advantages. Post-war assessments concluded that intelligence contributed substantially to Allied victory, though quantifying its exact impact remained impossible. How many lives were saved by stolen blueprints that improved air defenses? How many battles were won because intercepted communications revealed enemy plans? How many strategic decisions were improved by accurate assessment of enemy capabilities? The questions resist precise answers, but the directional conclusion was clear. Intelligence mattered. and the Allies were better at it than the Axis powers, particularly Germany, whose intelligence services were hampered by Nazi paranoia, interagency rivalry, and ideological blindness. The human stories within the intelligence war remained largely untold for decades after 1945. Security classifications kept files sealed. Participants maintained silence, bound by official secrecy oaths or personal discretion. Gradually, as participants aged and classifications expired, some stories emerged. Lindström's role became known to historians in the 1970s through declassified British intelligence files. Ant's identity was never confirmed. He remained a ghost in the historical record, known only by a cover name and his role in delivering documents. Perhaps he preferred anonymity. Perhaps he had no choice. His story destroyed with so many others in Germany's collapse. The final irony. The Flak 41 that inspired such desperate intelligence efforts proved less strategically significant than expected. German production difficulties, Allied bombing effectiveness, and the war's trajectory limited the weapon's impact. But the intelligence operation's value transcended any single weapon system. It demonstrated capability, established networks, refined tradecraft, and contributed to the larger Allied intelligence advantage that influenced countless operations and decisions. Success in intelligence often looks like this. Individual operations whose immediate results seem modest, but whose cumulative effect shapes outcomes decisively. Modern historians studying the Second World War's intelligence dimension face archival challenges. Records were destroyed deliberately or through neglect. Participants died without recording their experiences. Some stories were so deeply classified that documentation may never surface. Reconstructing operations like Lindström's requires piecing together fragmentary evidence, references in British files, Swedish customs records, interrogation transcripts of German intelligence officers, and the few interviews surviving participants granted. The picture remains incomplete, and gaps will never be filled. This is history's frustration and challenge. The past slips away even as we try to preserve it. The weapons development cycle initiated by stolen blueprints continued long after the war ended. Engineers who studied German designs during the conflict carried that knowledge into peacetime careers, developing weapons for the Cold War. Technologies pioneered in wartime, jet engines, guided missiles, radar systems, computer fire control, evolved into arsenals that defined superpower competition for decades. The Flak 41's high-velocity gun technology influenced post-war anti-aircraft systems and tank guns. The British 105mm tank gun, developed in the 1950s and still in service worldwide, owes conceptual debt to wartime study of German ballistics. Technology transfers across time and borders, carried by knowledge that survives the circumstances of its creation. Henrik Lindström died in 1978, largely unknown outside intelligence history circles. His obituary in Swedish newspapers made no mention of espionage, listing only his professional accomplishments in metallurgy and mining engineering. Those who knew his secret kept it, respecting his preference for privacy. In the end, he was a man who witnessed evil, possessed skills to oppose it, and chose action over safety. The consequences of his choice rippled outward in ways he never fully knew, touching lives across continents and decades, influencing events whose connection to one Stockholm night in January 1943 remained invisible to everyone except a handful of people who understood the intelligence war's hidden architecture. The story of one Allied spy stealing German gun blueprints and the weapon development that followed is not about heroes or villains in the simplistic sense. It is about the complexity of modern warfare, where victory depends on thousands of interlocking efforts across multiple domains. It is about the courage of ordinary people placed in extraordinary circumstances, making choices whose full consequences they cannot foresee. It is about the transformation of warfare itself during the 20th century, from contests of mass and valor to competitions of knowledge and capability. It is about the invisible threads that connect individual actions to historical outcomes, the hidden causality that shapes events while remaining obscure to those living through them. When we remember the Second World War, we naturally think of battles, Normandy, Stalingrad, Midway, the Bulge. We remember leaders, Churchill, Roosevelt, Stalin, Eisenhower. We remember technologies, radar, the atomic bomb, strategic bombing. But beneath these remembered elements lies a vast substrate of forgotten actions. The spy photographing documents, the engineer solving technical problems, the analyst connecting fragments of information, the soldier firing a gun whose origin story he never knew. These forgotten actions were no less essential, their participants no less courageous, their contributions no less meaningful. Intelligence work offers no glory, demands silence, and promises only that success will never be publicly acknowledged. Those who choose this path do so knowing their sacrifices will remain invisible. They work in shadows so that others can stand in light. They risk everything so that their nations might gain small advantages that accumulate into victory. They are the unseen warriors of modern conflict, as necessary as any soldier on any battlefield, fighting a war whose battles have no monuments and whose heroes have no names carved in stone. Their legacy is not in what we remember, but in the world their hidden efforts helped create. A world where the forces of totalitarianism were defeated, where democracy survived its greatest test, where the future remained open rather than foreclosed by Nazi victory. That legacy was purchased partly through courage we will never know, by people whose names we will never learn, who asked for no recognition and received none. They deserve remembrance nonetheless, these quiet heroes of the secret war, these engineers of victory won in darkness. Engineers of victory won in darkness.